Okay, so binomial, we are talking about a binomial random variable. How do we use the binomial probability formula? So what we do is we are, first of all, the context is that we're rolling dice and we want to know, do you know some games where getting doubles is desirable? Monopoly, right. So the probability, first of all, we have to understand the probability of rolling doubles on any particular roll. So let's figure out why it's 1/6. Why is the probability of rolling doubles 1/6? Well, how many total outcomes are there when you roll two six-sided die? 36, because it's just 6 times 6. So the total outcomes are 36. And then let's enumerate how many ways you can get doubles. It's either 1 1, 2 2, 3 3, 4 4, 5 5. Okay, so there's 6 ways. So 6 over 36 is 1/6. Okay, so doubles probability P is always 1/6. In this problem, it's fixed. So this is definitely a binomial situation. The number of rolls, so I'll highlight this for you. NP is really important, N and P. Number of trials, we're going to roll 4 times. They're all independent. What's the probability of getting 0 doubles, 1 double, and 2 doubles? So what I'm going to start out doing is I'm going to show you the formula and for all 3 of these at the same time, and I think you're going to see it. So for 0 doubles, we would go like this. It would be combination 4 choose 0, because we're having 0 doubles out of 4. And that, if you evaluate that on your calculator, which I can show you how to do later where that button is, you just get 1. Because there's one outcome and it's basically no double, no double, no double, no double. So then you multiply by the probability of getting doubles, which we get none of, is so 1/6 to the 0 power and 5/6. The 5/6 is just the complement. So this is the P and the 1 minus P. And how many times are we doing that? 4 times. We're only rolling 4 times. So that's the answer there. I'm gonna write all of them out, and I bet you'll see it. This would be combination 4 choose 1. That means we get 1 doubles, so that's 1/6 to the 1 power, and then 5/6 to the 3rd power, and then 2 doubles would be combination 4 choose 2 times. So we're getting doubles twice, so to the 2nd power, and we're not getting doubles twice, so that's to the 2nd power as well. Patterns. This exponent is always going to be the same as the number of successes. We have 0 successes. The probability of we get 0 doubles, so we want 1/6 to the 0 power. This 1 and this 1 are the same. We want 2 doubles. This 2 to the power 2 is the same. And then 4 times we're not getting doubles. Here, 3 times we're not. And these exponents always add up to n, the number of trials. So this is the same, so that it's on your notes, of saying combination n choose k times p to the k and 1 minus p to the n minus k. That's what I just did all these times. To understand it another way, if I were to list this, you actually knew how to do 0 doubles from the last chapter, because the probability of getting doubles is 1/6. So not would be 5/6 times 5/6 times 5/6. This is just the and rule, right? If we're going to get 0 doubles, the probability of not getting doubles is 5/6, and you want it to happen 4 times. So do you see how this answer is the same as what I wrote here? Because 4 choose 0 is just 1. 1 to the 6 is just 1. And so see, 5/6 to the 4th power is 5/6 to the 4th power. It's the same thing. And so you're really just doing this, but when we have 1 doubles or 2 doubles, there's different ways of getting that outcome. There's not just one way. There's different ways. You might get your doubles on the first roll. You might get it on the second roll. You might get it on the 3rd or the 4th. That's 4 times, so that's combination 4 choose 1. And there's 4 choose 2 different arrangements of getting 2 successes. So on your calculator, we'll have time to you'll have time to try these both ways on your calculator, but there's a shortcut. You can do this binomial PDF, and you give it the number of trials, the probability of success, and the number of successes. And so this one would be binom PDF. This one would be 4 1/6, and then you want 1 success, and this would be the same thing, binom PDF 4 1/6, 2 successes, and those are going to give you the same thing. So let's actually write the answers here so we can check. This is 0.482, so there's almost a 50% chance that you would not ever get doubles in your 4 rules. That makes sense, because getting doubles is difficult. There's only a 1/6 chance. This gives you 0.386, and this gives you 0.116. So our likelihood is going down of getting doubles more times. So that is, when you want it at a specific value, use PDF. Think P as in point. P as in just at a particular point. And now if I want a range of values, I don't want the hassle of adding all these up. So this is slightly different. Here we're trying to find the probability that we get greater than 2 rules. Okay. Now because this is discrete, that's the same as the probability x is 3 plus the probability x is 4. So we could just do them separately and add them up, or we could do the probability that x is greater than 2 is the same as 1 minus the probability x is less than equal to 2. And that there's a button for that, and that's called binomial CDF. Think cumulative, and it always does less than equal to. So think C for cumulative, and it always does less than equal to, just like in normal CDF, always does less than equal to. And you would tell it 4, number of trials, probability of success 1/6, and you want less than equal to 2. And that would be the fastest way. And so that's going to give you about 0.016. So there's only there's a very slim chance that you would get more than 2 doubles. So in fact, that's when you're suspicious. There's only a 1.6% chance of that occurring.